Dear participants, in this session we will be starting with experiment number 6 of section 1 IFVOC 105, in which we will be studying the Zener diode characteristics and definitely the application of Zener diode as voltage regulator. In the manual we have given a very brief theory where the two different types of breakdown in semiconductor devices has been discussed and their differences have been shown. And you can also find the symbol and photograph of the Zener diode. You can find the symbol to be very much similar to that of general purpose PN junction diode. However, the cathode is denoted as a Z here. That itself denotes that this is a Zener diode. Now you see here, this is the Zener diode and there is a black band here. So this black band shows you the cathode. Now, in order to perform the experiment, the components that you will require is one Zener diode and one resistance of 1 kilo ohm. That's it. Here, the basic characteristics of Zener diode that you should look forward to is one, what is the breakdown potential? The breakdown voltage is, you can see, 5.1 volt. That means the reverse breakdown of the Zener will take place at 5.1 volt. See, this is strikingly different from that of the PN junction diode, because in PN junction diode the reverse breakdown voltage is normally very high, and at the same time you need to remember, in case of a PN junction diode, if the reverse breakdown voltage is achieved, then the diode will go towards its damage or breakdown. Here it will not be like that. Here the Zener will be working as a voltage regulator. That means even if you increase the voltage through the Zener, or sorry, even if you change the voltage across the Zener, the output voltage will remain constant at 5.1 volt. That is the basic characteristic of any voltage regulator, that even if there is a change in input voltage, the output voltage should not change. However, there will be proportional increase in current. This is where you need to keep in mind what is the power dissipation capacity of the Zener diode. You can see the power dissipation is 0.5 watt. That means 500 milliwatt. So you need to remember that whatever current is passing through the Zener, that value should not exceed in such a manner that the power dissipation goes beyond this limit. This you have to remember. So you can decide, or you can decide what value of series resistance have to be taken. We require a regulated DC power supply to perform this experiment. We will be using a regulated power supply to the range of 0 to 30 volt DC. A digital ammeter we will require, 0 to 20 milliampere range ammeter we will use, and in case of the digital voltmeter we will be using a digital voltmeter of 0 to 20 volt DC range. Now you can find this is the circuit diagram to study forward characteristics of Zener diode. This is exactly similar to that of the circuit that we had employed for study of forward characteristics of a p-n junction diode. You can see here that anode of the Zener is connected to the positive terminal of the battery through this ammeter and the series resistance. The purpose of the series resistance is to resist or control the current through the Zener so that the maximum limit of power dissipation is not violated, and this ammeter is connected in series to measure the current through the Zener. Afterwards you can find we have to check the potential or the voltage across the Zener. That's why we have connected this voltmeter. Now this is the circuit for studying the forward characteristic, and in reverse characteristic everything remains the same, only the Zener is connected in reverse biased condition. Now once you have connected the circuit, so far the procedure is concerned, in the forward biased condition, after you are ensured that your circuit is connected properly, then you gradually change the voltage across the Zener in steps of zero point 0.1 volt, and you do this up to 5 volt. Record the corresponding values of current and tabulate them in the observation table. In the reverse biased condition, you apply the reverse voltage in 0.5 volt step and you go up to 8 volt or 10 volt. You note down in each case what is the value of current, that is Zener current. Now once you are ready with these readings, you can go for plotting the graph. So you have to take a graph paper, and if everything is alright, perfect, then your graph should look like this. In the positive x-axis, you note down the values of positive voltage, and in negative x-axis, the values of negative voltage. In positive y-axis, the values of positive forward current, that is forward current, and in the negative y-axis, you have to note down the reverse current. That's it. Now, once we are complete with the study of the Zener diode characteristic, now comes the operation of Zener diode as a voltage regulator. What is the basic operation of a voltage regulator? A voltage regulated has to negotiate in such a manner that even if there is a change in the input supply, the output voltage should remain constant, or if there is a change in the load, the output should remain constant. This is the very basic operation of a voltage regulator circuit. Remember that you can have current regulator also. In that case, voltage will vary, but current will remain constant. But in case of a voltage regulator circuit, you need to have constant voltage at the output, irrespective of the fact that there can be change in input supply or there can be change in the value of the load. Okay, therefore, in these two cases, we have to study the two different types of characteristics of a voltage regulator. In any voltage regulator, actually we need to study these two characteristics. One is line regulation characteristic and other is load regulation characteristic. When we are performing such measurements, this is the circuit for that. You can see in front of you that there should be a variable supply. The Zener should be connected obviously in reverse bias. There should be a load connected in parallel to the Zener, and finally there will be a voltmeter through which we can measure the output voltage. Okay. Now you see that when we are studying the line regulation characteristics, when we are studying the line regulation characteristics, then we need to keep the load value constant. We need to keep the load value constant, and we need to continuously vary the input voltage. And for each value of input voltage, we need to note down the output voltage. Okay. And in case of load regulation, you need to keep the supply voltage constant, and you have to check the changes in output voltage with respect to changes in load. Okay, so this you have to remember. Now, whenever you are doing that, you have to take some sets of reading. Suppose we are changing for line characteristic, you are changing the line voltage for a fixed value of load. You have to take at least 1, 2 and 3. different values of load, and you have to note down the output voltage. Again, for load characteristics, you are changing the value of the load where input is constant. Okay, so you can see the input value, constant value. You can have reading for one or at least two different voltages. You should take the reading so that you can come to a solid conclusion. Now remember that you have to take two different, you know, calculations. One is the load regulation of the voltage regulator, and other is the line regulation of the voltage regulator. This is the AP Malvino and Bits book that I have given to you. You can find that load regulation indicates how much the load voltage changes when the load current changes. And the definition is given through a mathematical equation that you have to remember. That load regulation is given with this particular formula. You can see it is VNL minus VFL divided by VFL into 100. That means it is taking the percentage value. What is VNL? VNL is the load voltage when there is no load current. The load voltage when there is no load current. And VFL is the load voltage when there is full load current. This you have to remember. Now you see one example is given that if we have a power supply where no load voltage, no load current voltage is 10.6 volt. So that means that you can see the IL, that means load current is 0 here. So you have got the voltage of 10.6 volt, and with full load current, that is 1 ampere, you have an output voltage of 9.25 volt. So your load regulation becomes 10.6 minus 9.25 divided by 9.25, and it will be 14.6%. Now let us go for line regulation. Remember that it may so happen that your input supply is varying for some reason. So that we have to consider now. Now you can see the line regulation is given as the load voltage with high value of input, that is the line supply, and load voltage with low line supply, low value of line supply. So that will be VHL minus VLL. Okay, VHL minus VLL. The VHL is high value of input supply. At that time, what is the load voltage? And then there is low value of input supply. Then what is the load voltage? In that way, you can determine the line regulation characteristic of the regulator. So we will first go for the simulation, and we will just be seeing the behavior, and we will be performing the actual experiment. Remember, while performing the actual experiment, I will not go for each and every reading. I will just show you the characteristic, and whenever you are actually performing the experiment, you will be noting down the values, you will be drawing the curves like that. Okay, so let us now go for the Zener diode. Okay. So first we will be going for Zener diode characteristics. So whenever we are talking of Zener diode characteristics, we are very much interested in the reverse characteristics of the Zener diode. Because in forward characteristics, it is accepted that it will work simply as our PN junction diode. Okay. So let us go for choosing the diode. I will be choosing this 1N4733A. You can see the breakdown potential is 5.1 volt. Okay. Now what we will do, there is a constant RS, it is given over there. I will be simply changing the resistance which is connected across this supply. So this is the battery, and here there is simply a potentiometer. Okay, I will be simply changing the wiper position of the potentiometer. Okay, so that we can have the change in voltage that is being applied across the Zener. So we will enter this resistance value, we will add to the table. You can see as we change the resistance value, the voltage across the Zener changes in the experimental table. So we will go like this. We keep on changing the values. You can see now we have reached 5.1 volt. That is the breakdown. So we have added it to the table and we will plot. You can see here that this is the voltage across, this is the voltage in the x-axis, and this is the current here. Dear participants, in this session we will be studying the Zener diode characteristics while performing the actual experiment. You can see we have prepared this simple circuit for the purpose of this experiment. You can find here, this is where from we apply the input supply. The positive terminal is connected directly to a series resistance that restricts the current through the Zener, and you can find from the series resistance we get this terminal for the ammeter, and the negative terminal of the ammeter is connected directly to the anode of the Zener. You can see the black patch is on the common side. So now the Zener is in forward bias. Okay, the voltage across the Zener, you can see the parallel tappings are there. The voltage across the Zener is measured through these two terminals. So now we will build up the circuit. It's a matter of minutes only, but we have to remember that this meter is displaying the voltage across the Zener, and this meter is displaying the current through the Zener. Okay, so first of all we will be connecting the positive terminal of the ammeter, then the negative terminal of the ammeter, then we will be connecting voltmeter for reading voltage across the Zener, and finally we will be connecting our power supply. Okay, so what we will do, we will simply increase the voltage across the Zener in steps of 0.1 volt. Okay, and we will see that how the Zener behaves. It is expected that the Zener will have a forward breakdown which is just similar to that of a PN junction diode, and then the Zener current will increase. Before that there will be no increase in Zener current, or there will be no current through the Zener as such. Okay, so I will increase. Yeah. Okay, so you can see this is 0.1 volt applied across the Zener, and there is no current. All right. Now let's go a bit forward. You can see it is 0.2 volt. Sorry, yeah, it's 0.2 volt or 0.3 volt. You can see that voltage across Zener is same as that of the supply, but there is no current. 0.4 volt, still there is no current. You can see still the current value is 0. Now you can find, I have made it 0.6. There is some current, as you can find. I'll make it 0.7. You can see 0.68. Now the current has started increasing. Now it's 0.7 volt. The current has started increasing. Now you see, I will gradually change the voltage across the Zener. However, you may very easily find that this value, it has become almost constant. However, the current is increasing in proportional to the voltage that is being applied. That means the Zener is behaving
similarly to that of this forward biased PN junction diode. Okay, now we will simply reverse the Zener. That means we will connect the Zener in reverse bias. For that I will be changing the terminals of the Zener. So that's fine. I have just changed the terminals of the Zener. You can find here. Now the Zener is reverse biased. Okay, you see the black patch. All right. We will apply the supply here, and now we will be changing the voltage in steps of 0.5 volt, or we can go for 1 volt also. There is no problem absolutely. Yeah. You can see there is 1 volt across the Zener. There is no Zener current. I'll go for 2 volts. You can see here 2 volt is applied across the Zener. Still there is no current. Three volts, no current. Now I have applied 4 volts across the Zener. Still there is no current. I will go for 4.5 volt. Now you can see some deflection is observed in the current meter. Okay. Now we will be going for 5 volt. And you can see here the current is increasing because we are nearing the breakdown. Now you can find this voltage. It has got almost constant and the current is increasing. So I will be slowly increasing the voltage, applied voltage. You can see although the applied voltage is right now around 7 to 18 volt, the voltage across the Zener is 5.08. That means 5.1 itself, and the current is now flowing through the Zener. That means the reverse biased, the behavior of the Zener diode in reverse bias is proved here. We can see that although we are increasing the reverse potential, the voltage across the Zener is constant. Okay, so now what we will do, we will see the line and load behavior of Zener as a regulator. For that we do not need this ammeter, okay, but still we will keep it there on the circuit. We will retain it in the circuit, and as a load I will be connecting this arrangement. You can see here this is simply a potentiometer. Alright, and we will be using two terminals, the center terminal, that is the wiper terminal, and one of the end terminals for this purpose. So I will be connecting it across the Zener. I will be removing the supply, and since this is simply a variable resistance, there is no consideration of polarity, so we can simply supply it in parallel to the Zener. Okay, so you can find here we have connected this stuff, that means this load. All right, you can find here this is the load, and rest of the things are there. I will just shift a bit. Okay, now what I will do, I will adjust the load to a certain value. Okay, you can see I am rotating this. I am adjusting the load to a certain value and I will keep that constant. Now I will be giving the supply. I will gradually increase the supply. Here the load is constant. I will simply change the line value. Okay, so here we are studying the line characteristic. So initially the voltage will increase across the Zener till it reaches 5.1 volt. Now you can see I am changing the value of line voltage, but there is no change of voltage across the Zener. That means the line regulation characteristics of the diode is absolutely perfect. Now what I will do, I will keep some voltage constant above the value of 5.1. Maybe I will keep 10 volt constant, and then I will be changing the value of load slowly. We have to check whether there is any change in the output voltage across the Zener. You can see I am changing the load. You kindly look at this white spot. Okay, now it's shorted actually. Yes. You can find, because you should not short it, then entire current will pass through that only. You can see here that even if the load is changed considerably, this is a 10k pot, you can find the voltage across the Zener is constant. So what does that mean? That means that even if the load changes, the output of the Zener, output voltage of the Zener is maintained at a constant value. Alright, again you can see I have kept the load at certain value and I will change the line voltage. You can see the current changes. However, the voltage is keeping constant. I will go a bit higher maybe. I am at around 18 volt, but still you can see the current has increased, but the voltage is remaining at constant value. So this shows that the Zener is an excellent voltage regulator. So for the line regulation behavior and load regulation behavior is considered. That's all with it. Whatever confusions that are developed in your mind, kindly put it in the comment box so that we can get back to you with the solutions. Thank you.